Good morning, good morning, good morning. How's everybody doing today? Good to see you, April, AK. Jordan, good to see you. Amber, Casey, hello. Ryan, Kingy, hello. Shavoni, good to see you. Thanks for coming today. How's everybody doing? Can't believe we are now in week 5. So we're a third of the way done with this semester. I don't know about y'all, but I'm pretty doggone excited about that. I hope the A&P exams went well this past week. Some people were talking about those. I hope you did okay. Good to see you, Suah. Good to see you, Jennifer. Fantastic. Wow, good crowd today for the class. It's good to see everybody. I hope y'all are doing well. Any questions about this week's content, this week's homework? We finished up the first exam. Everybody did great at that. So things are going really well on my end. I hope they're going well for you also. Anybody have plans for the weekend? Any plans for the weekend? Something fun to do? I've got lots and lots of homework myself. Okay. All right, well, let's go ahead and get started with today's lecture. So, Chapter 5 is Sensation and Perception. And yesterday we focused on sensation and perception in the visual system. Today we're going to talk about the other senses. And you can use them when you're at the soccer game this weekend with the kids, April. I guess you're going to be doing the travel ball thing, aren't you? Fantastic. Good for you. Good for you. All right. So if you remember from, if you remember, hello, Make a Fun. I'm not sure who Make a Fun is, but it's good to see you as well. So if you remember last week on Tuesday, we were talking about sensation and perception as being two processes. The full sensory experience that we all have involves the recording of neural information onto our brain, right? And that's the information that we receive from these receptor cells. And you then have to make meaning of these patterns of neural activity, which is the perception process. So remember, full sensation requires, the full sensory experience requires sensation and perception. We're going to start by going back to this chart that I sent you on Tuesday that we looked at. Remember, we have 5 sensory cortices. We have the 2 cortices in your frontal lobe, the olfactory cortex and the gustatory cortex, so taste and smell in the front part of your brain. Auditory cortex is right down here in the temporal lobe, and I like to think of the auditory cortex as, remember, the temporal lobe is where memories are, and if you think about where do you hear things that you remember, so I always think of the auditory cortex as being in the temporal lobe. Remember, your somatosensory cortex is actually in the front part of your parietal lobe, and then we have an occipital lobe at the back of our head, and that's where our primary visual cortex is. As I suggested to you, all of these sensory cortices receive input through the thalamus, with the exception of smell, which probably developed so early in the brain's development process, in the evolutionary process, that it developed before we even had a thalamus, which is what the theory is on that. Okay. Now remember, not only do we have these primary visual or these primary sensory cortices, but we have association cortices. And these association cortices help us create more full, complex sensory experiences. So remember, I talked to you about the different things that are processed in vision. All of these primary sensory experiences are put together in your association cortex, so you can see what it is, the object it is you are looking at. And then the sensory and the sound and the auditory and your other cortices also combine together in larger association areas. So remember, association cortices are areas of the brain that combine basic sensory experiences to help form perceptions of objects. Okay. Hi, Erica. Good to see you. Thanks for coming. Better late than never. You didn't miss much. We just talked about what we were going to do for the weekend. Looks like April's got some soccer games to go. I reintroduced the idea of sensation and perception as being two parts of the sensory process. And then again, we are back to the cortices to sort of explain to you the different parts of the brain where sensory experiences are perceived. Let's talk a little bit about hearing. Okay, so hearing involves mechanoreception. So your hair cells are mechanoreceptors. That is, they respond to pressure by moving. And these hair cells are your sensory receptors that receive mechanical information and turn it into patterns of neural activity. Okay, so if you would look at this picture right here at this picture right here. There are going to be pictures like this for all of your senses in the book, and so please go to those and take a look at them. If you look at the farthest picture right over here, closest to me, not the lady with the saxophone, but the other one, but you'll notice that we have the right auditory cortex and the left auditory cortex, and you'll see how the nerve pathways come down. They're going to come through the thalamus, and then they're going to connect to this thing called the auditory nerve. So this is how your ear is connected to your cortex. And remember, sound is processed through your thalamus, just like most of the other senses. So you have this big structure called an ear, and you have this soft pinna thing right here. And its job is just to capture and focus sound down into this auditory canal that you have. So you have a big floppy pinna right here, and this outside part of your ear is designed to catch sound waves and to transmit them down into your auditory canal. All right. Now, you'll notice that we have an eardrum. It's basically a membrane structure down at the bottom of your your auditory canal that vibrates with whenever sound pressure comes down your auditory canal. And so that eardrum vibrates. Now it's connected to three teeny tiny bones located inside your middle ear: the hammer, the anvil, and the stirrup bones. Anybody ever heard of the incus, the malleus, and the stapes? These are the smallest bones in your body, and they are located inside your ear. They are touching your eardrum, and these three little bones then vibrate and cause vibration to occur on your a little thing called an oval window attached to your the middle of your ear. Now, what this does is this magnifies the vibrations that come in your ear by 10 times. So you have this big eardrum vibrating. It causes these bones to vibrate, which cause this teeny tiny membrane to vibrate. Because we're going to a big membrane to a small membrane, the vibration frequency and the vibration intensity is actually multiplied. So these inner ear bones actually cause the vibrations that you think of as sound to become magnified. Now, down here in the bottom of your middle ear, they connect to this structure called a cochlea. Okay? Now, this cochlea is in the interior of the ear, and if you pull it out, it's like a big long tube, and it's rolled up. And if you see the middle picture here, they've kind of unrolled it a little bit, but it's a big fluid-filled tube, okay, that has a membrane called a basilar membrane, and and close to that basilar membrane are these hair cells. And so as your interior ear bones vibrate, they set up waves inside this little cochlea, waves of water pressure, fluid pressure. And as this fluid moves, it causes this basilar membrane to move, and this basilar membrane pushes on these hair cells, okay? And that's how sound is created. So you've got sound waves coming in the ear. They're captured by the pinna, and they're directed down into the auditory canal. They cause your eardrum to vibrate, which is connected to 3 teeny tiny bones, which magnify the intensity of that vibration, and vibrate onto a little window called an oval window that's attached to this cochlea structure. These vibrations then cause the fluid and the membrane inside that cochlea to move, and that causes it to move hair cells, which then your brain perceives as sound. These hair cells then transmit the information out of the ear through the auditory canal. It travels up through this auditory nerve, through the thalamus, to your auditory cortex. Okay? Now, here's the deal. What I want you to know is, let's go back and revisit the word transduction. Transduction is the process of turning physical energy into patterns of neural activity. So it's those hair cells located in your cochlea that engage in the transduction part of this process. Okay? Holy cow, we've got Etta Swider in the class. Etta Swider is a former student of mine that now lives in Ohio. She's checking back in to say hello, and it's good to see you, Etta. Thank you very much for coming into class. Thank you very much, Etta. I appreciate that. I hope everything's going well for you, and you're getting a lot of good craft beer where you're living up in Ohio. We're just talking about sensation and perception. Yanan, good to see you. Thanks for coming in. And Erica's dropped off the kids. That's why you were a little late. I understand the mother thing, Erica, for sure. Well, thanks for coming in, Ed. I'm going to get back to lecture now, but it was good to see you. All right, so remember, transduction is the process of turning mechanical or physical energy into patterns of neural activity. And so your book's going to describe the transduction down here by showing the hair cells, how they're located near the basilar membrane, and how they vibrate. Now, here's the thing. When sound waves come into your ear, the force of the sound waves creates the loudness. Okay? So the magnitude of the sound waves that come in, how big they are, creates what we will call the perception of loudness. Okay? Now, the speed of these waves, or the wavelength, is what determines the pitch of the sound. So really, if you think about sound information, we take in two broad characteristics of sound waves. Their intensity, loudness, if you will, and pitch, which is frequency of the wavelengths. All right? Now, I want to talk a little bit about frequency. How exactly do we record frequency in the ear? There appear to be sort of two ways in which this happens. In your book, or the books that I've read on sensation and perception, focus more on one particular way. Now, if you'll notice, this cochlea is long. It's kind of long. You know, it might be this long, but it's wrapped up into a circle, if you will. All right? Now, if you unwrap it, you'll notice that there's a basilar membrane that runs down the complete end that runs all the way down the length of this cochlea. And what happens is the vibrations that occur in the different locations are used to process pitch information. So the hair cells, if the hair cells close to the oval window vibrate, you get high-pitched sounds. If the hair cells at the end of the cochlea vibrate, you get low pitch sounds. So we can think of one way of producing pitch in our ear is by what we might call the location model. The location model. It depends on where in the cochlea the hair cells vibrate. And there is some evidence to suggest that the speed of the vibration also affects your perception of pitch, with faster vibration of the hair cells creating higher pitch sounds than lower frequency vibrations of these hair cells. And so these hair cells are the receptor cells whose job is to transduce mechanical energy into patterns of neural activity. This information then travels to your auditory cortex, where you begin the interpretation process we think of as perception. Okay? Now, I do want to stop 1 minute and talk to you a little bit about your sense of balance. We also have a sense of balance. We typically don't think of it as one of our 5 senses, but knowing how you are oriented in the world is an important sense that allows you to walk around. You know when you're upside down, you know when you're laying down, you know when you're standing right up, or when you're bending over. All of these positions are perceived initially by these 3 structures located in your inner ear called the semicircular canals. And over on the far left-hand side of this picture, you can see these semicircular canals. They are 3 fluid-shaped canals that are sort of oriented in different directions. So you've got 2 of them facing this way and then 1 of them facing this way. And so you have these fluid-filled canals, and they also have hair cells in them as well. And what happens is when you bend over and move your head, this fluid runs around these semicircular canals and makes the hair cells bend over. And so the fluid moving inside these 3 canals allows you, is the information that allows you to figure out how you're oriented in the world. All right, and this sense of balance is something that you learn as an infant. You learn to interpret these signals in your inner ear, and that gives you a sense of balance. Now, the information from the semicircular canals does not travel to the auditory cortex. The information from the semicircular canals travels to the cerebellum, and the cerebellum is where your sense of balance is processed. In process. Does that make sense, everyone? So what do I want you to know from this slide? I want you to know the function of the 3 bones in your inner ear, magnifying that vibration. I want you to know what 2 structures are in the cochlea, the basilar membrane and the hair cells. And I want you to know that pitch is determined by which hair cells vibrate, and loudness is by the absolute magnitude of the sound waves coming in your ear. And I want you to know that the semicircular canals process balance information and send that to the cerebellum. And of course, you need to know what the word transduction means. Any questions about the sense of hearing? Okay. Oh, actually, here you go. I'm sorry. I talked about that before flipping over to this slide. I got a little excited. So here are the qualities of sound: loudness, pitch, and location. So as I said, perceiving pitch depends upon the sound wave frequency, how fast these little waves are moving together. And we have 2 theories: the place coding, which is which of those hair cells in the cochlea vibrates, right? And so vibrations at the beginning of the cochlea produce the high pitch, vibrations at the end of the cochlea produces low pitch, like I said. And there's also a suggestion that the speed of the hair cells helps demonstrate the pitch. Loudness is determined by amplitude sound wave. So the bigger the wave is, the more pressure it creates on your ear, the louder you hear the sound. And then one final thing that I did want to mention is we also localize sound. So if you remember, Ben Underwood was really good at figuring out where things were and the sizes of things, and he did that by reading the different sound waves coming into each of his ears. So sound is localized based on differences in timing of the sound processing between the two ears, and also the loudness between the two ears. So you'll notice that there's a picture of a fellow standing underneath me, and he's got the sound coming from sort of towards his left side, and he's got his head turned away from it. So the sound waves reach this ear before they reach the ear away from the sound. And the difference in timing between those, when those two sound waves are processed in your cochlea and sent to your auditory cortex, are used by your brain to judge where sounds are coming from. If you remember on Tuesday, I talked about monocular depth cues, that is, cues your brain uses in order to judge three-dimensional distance. Well, if you think about it, localization of sound is also another perceptive ability. You're getting sound in this ear and you're getting sound in this ear. Your brain is judging the difference in when it hears the same sound in both ears to make a judgment about where that object is in your environment. Okay? And so the three basic qualities perceived by an ear are pitch, loudness, and sound localization. And from those basic processes, you create an entire sensory experience of the things you hear and the things you understand. I didn't get any questions, so I hope I'm making sense, and I hope everybody's getting what I'm talking about. Let's talk a little bit about taste. All right, so taste is processed. Transduction of taste is processed by these receptor cells located in taste buds on your tongue. The sense of taste and the sense of smell are both processed by what we will call chemoreceptor cells. And those are receptor cells that respond to chemical molecules. So molecules cause these receptor cells to become depolarized and generate action potentials. So if you've got a sweet receptor cell and a sugar molecule interacts with it, it causes that sweet receptor cell to generate an action potential, which your brain perceives as sweet, or it could be salt or bitter or whatever. Now, we have these receptor cells that transduce chemical stimulation into action potentials. They're located in the 8 to 10,000 taste buds that we have in our mouth. Now, the taste buds right here collect the information. It then goes down underneath your tongue and follows out through your jaw, the lower part of your mouth, and it goes through the brainstem, up through the thalamus, and into your gustatory cortex, your taste cortex. Again, taste is processed through the thalamus, just like most other senses. All right, now, here's the deal. Some of you may be super tasters. That is, you have 6 times the normal number of taste buds. If you go in your book, they have a short demonstration where you can figure out whether or not you are a super taster. Okay, if you're the kind of person that doesn't like strong foods, like if coffee grosses you out, or maybe collard greens, or some other leafy green vegetable, if strong tastes are something that really turn you off, you may be a super taster. I like sweet taste too, but it is bad for you. You've got that right. You know, it's kind of interesting, Etta, and not to bring this up, please don't feel sorry or say anything like this, but I had cancer in the throat this past year, and they had to radiate my throat area for 7 weeks, and I completely lost my ability to taste anything. I couldn't taste a stinking thing. Everything tastes like cardboard nothing. I could eat sugar, I could eat sour, I could eat salty, and I tasted nothing. And what happened, the doctor told me it wasn't the taste buds that were damaged, but the neural pathways leading out of my mouth. The radiation therapy caused swelling and damage in and around these neural pathways. And so this swelling kind of shut off these neurons so that they couldn't work. And so the sensory information was coming in my tongue, but it wasn't getting anywhere past here. So I was not able to perceive any taste at all. Now, Etta mentioned sweet, and the only reason I talk about this is because I've gotten some of my taste back, but I still can't taste anything sweet. I eat ice cream, it tastes like cardboard to me. I eat a chocolate bar, I can't taste any sweet. So most of my senses have now come back, with the exception of my sense of sweet. For some reason, it hasn't come back yet. No, it's not. And everything tastes really, really bizarre, Etta. Things, in fact, if I closed my eyes and took a bite of something, I probably wouldn't be able to tell you what it is I was eating, because everything tastes outlandish and weird. And chicken doesn't taste like chicken to me anymore. And beef doesn't taste like beef. And nothing tastes like it's supposed to. Now, and what I believe it is, it's because part of my sweet taste has not come back yet. So let's think about this for a minute. There are five main tastes. There are five main taste receptors on your tongue. You have taste receptors that respond to molecules like glucose and sucrose and fructose. And those taste receptors give you this sense of sweet. So anytime these molecules, so I still love my dad. I was telling Etta that I was able to eat my dad's spaghetti for the first time. My dad makes the worst spaghetti in the entire world. But since I lost my taste, I can go over to Dad's house and I eat his spaghetti now. And I'm like, wow, Pops, this is some good stuff. And Dad thinks that his spaghetti recipe has gotten better, and it hasn't. I just can't taste anything. So it's kind of funny. I can't believe you remember that, Etta. That's a funny story, right? So some of these taste receptors on the front of your tongue respond to glucose and sucrose and other sugar molecules. They give you the sense of sweet. Now you have some other receptors located, and this is actually at the sides of your mouth, and they respond to hydrogen ions, so loose hydrogen ions, and they give you the taste of sourness. Now you have some other taste receptors on your tongue that respond to sodium ions, and so they give you the taste of salty, if you will. Now, it turns out that there are several different kinds of molecules that create this sense of bitter. And bitter is processed on the back of your tongue. And there are lots of different molecules that give you the bitter taste. Almost everybody universally hates the bitter taste. So it was thought that the taste of bitter developed sort of as a protection against being poisoned. Because a lot of molecules that will poison you are the ones that come off tasting bitter. So it's actually thought that bitter sort of developed as a way to protect you from poisoning yourself. And then there are some receptor cells that respond to glutamate, and they give you the sense of umami. And if any of you are wondering what in the heck is umami, umami is that sort of that pot roast taste, that savory, meaty, salty, mushroomy taste that that most of us like, and that's called umami. So if you think about it, well, and there you go, Etta, that's why, if you remember when we talked about memory in chapter 7, I'm going to suggest to you that one of the ways in which you can improve your memory is by creating funny images. Things that are funny activate our amygdala, which activates our hippocampus, which allows us to store a stronger memory trace. Very good. Exactly. Etta remembers everything. Now, the weird thing is, if you think about it, we have these 5 basic tastes, but there are more than 5 tastes in the world. There are tons and tons of tastes. So really, you can think of your mature taste as the combination of these different receptors being activated. And one of the reasons, so 3 months ago, I couldn't taste anything and everything tasted dull. And it was easy to eat things because nothing really had any taste. It wasn't very good and I didn't enjoy it, but it was edible. Now, most of my tastes have come back, with the exception of my sweet. I can't taste anything sweet at all. And so if you think about it, every complex taste that you have has a little bit of sweet, a little bit of salty, a little bit of umami, maybe even a little bit of bitter or sour. And so we have these combinations. Well, I still have one perception, sweet, completely out of the equation. And so when I taste something, the combination of sensory receptors isn't right. And so even though pizza isn't supposed to be sweet per se, the fact that I can't taste the sweet aspects of the pizza sauce kind of ruined the whole taste of pizza for me. And so when I eat things, none of them taste right because the right receptors in my mouth aren't working just yet. And so now I have very, very vivid senses, but the senses, so I taste things really strongly, but they all taste completely wrong because for some reason the pathway from my sweet receptors hasn't repaired itself yet. Okay? Now, I will tell you that taste is a very important part of the hunger process. When we talk about motivated behavior in chapter 11, we're not going to focus on taste as much as a part of the hunger process. But it turns out if you can't taste something, if something doesn't taste good, you are not nearly as hungry as you normally would be. And one of the things that I'm actually having trouble with right now is trying to regain the weight I lost this past spring. And I can't eat a lot because everything tastes so bad. So I might have 3 potato chips and then I'm done with potato chips. I might have half of a hamburger and then I'm done with the burger. And the weird thing is, because the taste isn't enjoyable, I'm not as motivated to eat. So being able to taste things is a very important part of the eating process. Anybody have any questions? I want you to know that your taste receptors are located in taste buds. They transduce chemical energy into patterns of neural activity. You have 5 main taste receptor types responding to different molecule types. Okay, and some people are super tasters in that they have tons more taste receptors than non-super tasters. I hope that makes sense. That's the sense of taste. And again, taste, just like vision, just like hearing, is processed through the thalamus. Now, smell. Smell is the only sense that is not processed through the thalamus. It looks like the sense of smell, chemoreception, may have developed prior to the full development and evolution of the thalamus. So your sense of smell doesn't go through your thalamus. However, your sense of smell is intimately connected with your hippocampus and temporal lobe. And this is why a lot of people have memories when they smell things. I'll bet some of you, in fact, let's do this. Can some of you tell me what's a food that reminds you of your mom or your grandma's cooking or your dad or your grandfather's cooking? Does anybody have a food that reminds them of Christmas or their family? I'll bet each and every one of you have a food that when you smell it, you go, wow, I remember this, right? And that's because our olfactory nerve, the one coming from our nose all the way to our auditory cortex, is connected with the temporal lobe, so it smells often evoke memories. John, bread. Bread makes you think of, fresh bread makes you think of grandma? Absolutely. Whenever lasagna for your grandma. Oxtails. Holy cow. Jordan, are you from the Caribbean? Is that why oxtails? We don't eat a lot of oxtails here in the southern United States. At least I don't think we do. I'm not sure. That's interesting. So we got bread, lasagna, and oxtails. Yes, bad spaghetti makes me think of my dad. Whenever I smell bad spaghetti, I go, oh man, God, that takes me back to my pops. Okay, so now, yes, I remember that smell of cakes at Christmas. My husband's family loves oxtails. Oh, they're from South Africa. I see. I did not know that oxtails were a South African delight either. Now, floating chemicals are called odorants. Odorants. And so these chemicals that are floating around float into the nasal canal, into your nasal passages. You've got these little hairs located inside your nose that sort of waft and further move these odorants up into your nose. And when you get to be an older man, these nose hairs start growing a little bit long. Somebody tell Etta what an oxtail is. Okay? And so these odorants then float up into your nerve. And if you'll notice the picture right here in the middle of this picture underneath me, you'll notice that you have these olfactory receptor cells that are located right here in the top of your palate, right up here in the top of your palate. And these olfactory cells have little projections that go back down into your olfactory epithelium. And these olfactory cells respond to chemicals called odorants that are floating through the air. So the olfactory receptors are located in a mucus layer in your nose. And it turns out that we have 350 different types of odorant receptors. So there are 350 different molecule shapes that can be perceived by your olfactory receptors. And it's the patterns of these different types of receptor cells that lead us to be able to distinguish millions of smells. And so as a child, you will learn that when these 5 odorant receptors are activated, that smell is spaghetti. When these other 6 odorant receptors are activated, that combination of smells is coffee. And then maybe there are 15 other odorant receptors. Maybe some of them go with coffee, some of them go with spaghetti, some of them go with birthday cake. When you put all these combinations together, you smell pot roast. So we have 350 different types of receptor cells that respond to 350 different chemical shapes, all right? And it's the combination of these different olfactory receptors that we then learn to perceive as millions of different tastes, okay? Now, you'll notice that the olfactory receptors are in this structure called an olfactory bulb, all right? And the olfactory nerve travels through parts of the emotional and memory system, the amygdala, the hippocampus, and the temporal lobe. And this is why smell often stimulates memories. Made of cow stomach. Oxtails, cowtail. You know, actually, I did go to a Caribbean restaurant and had the oxtails, Etta, and I thought it was pretty tasty. Would you say it kind of tasted like pork in a way? Those of you who know AK, April, tell me, do you think that's sort of a porky or a beefy taste? Now, here's the thing. All of your senses, if you think about it, are very, very localized. So all of your visual receptor cells are in your eye. All of your auditory receptor cells are in your inner ear. All of your taste receptors are on your tongue. And all of your chemoreceptors, your olfactory receptors, are located right here in this one part of your body. But if you think about it, your sense of touch is systemic. You have sensory receptors here, you have sensory receptors here, you have sensory receptors here, you have sensory receptors all over your body. So the sense of touch is different from the other senses in that we have touch receptors all over our body, not just in one part of our body. And these sensory receptors all transmit information up through the spinal column, through the brainstem, through the thalamus, and to the somatosensory cortex located at the front of the parietal lobe. Okay? Now, we have different kinds of, and these receptors respond to pressure and movement. So we're going to call these types of receptors mechanoreceptors. And they record different types of force that are going on. Some of them report vibration. Some of them report stretching, right? Some of these receptors are what we call thermoreceptors. They're located in your body, and they measure when a body part's temperature is different than the core temperature, right? So if this part of your arm is higher in temperature than 98.6 degrees, your brain tells you you have something warm right here. Okay, so we have warm receptors, and then we have nociceptors that respond to breaks and damage in the skin that give us the sensation of pain, if you will. So, what are the different types of receptors that we have? We have thermoreceptors, that is warm and cold receptors. We have hair receptors, which do which do movement on the skin. They tell us whether or not things are moving across our skin. We have vibration receptors. We have fast pressure receptors that are more like pain. We have light, slow pressure, which is going to give us a sense of itching. Okay, and then we have stretch receptors so that our body can tell where our body parts. So when I move my arm right out this way, my stretch receptors in my elbow activate. And these stretch receptors tell my brain, hey, Chris's elbow is stretched out. And so that allows me to tell where my body is. So, in a sense, these receptors tell us when things are touching us. They tell us whether or not things are warm. They tell us whether or not things are damaging us. And they also tell us where our body parts are in space. So I don't even have to look. I can feel my legs down below me, right? And so, in a sense, all of these different sensory receptors are located all over your body, and they sort of give you an idea of how your body is feeling. Is it warm? Is it moving? Is it itchy? Is it in pain? Right? And so we have these kinesthetic sense, all right, which is ability to feel the relative location and movement of your body. Again, this is processed by your cerebellum. And stretch receptors provide information about your body's movement and position. Okay. And then we have different types of pain receptors. Different types of pain receptors. Okay. Now, it turns out, bye, Etta, thanks for stopping by today. And so we also have different kinds of pain. If you've ever been jabbed by something or cut by something, that information is transmitted on your fast fibers. Now, what do we mean by fast fibers? You know what? They have thicker axons. Fast fibers have thicker axons. And so these thicker axons transmit information super fast from your body part to your brain. And these fast fibers let us know when our body integrity has been damaged. So if you've been cut, or if you put your hand on a hot stove. And if you think about it, this information needs to travel super duper fast so that you can move away from whatever it is which is damaging your body. Okay? Now, we also have nociceptors which transmit dull aching pain, that kind of pain that won't go away. These are slow fibers, and these slow fibers have thinner axons, and so it takes the information longer, the aching information, longer to get from our body to our brain than it does for the sharp pain information. Okay, now I don't know if any of you have ever stubbed your toe before. Have you ever noticed that when you stub your toe, you can tell you have stubbed your toe a half a second before it starts hurting? Has anybody else had that experience like me? Or if you've ever put your hand in hot water, you can feel the water a second before you feel the pain from the heat. If you've ever had that experience of knowing, uh-oh, I stubbed my toe, it's going to hurt, and it takes just a second for the pain to kick in, that's because the touch information is beating the pain information to your brain. Okay? That's because stubbing your toe is being processed by several different mechanoreceptors that are all sending that information to the brain. And the touch information travels much quicker than the pain information. So you can tell you are going to hurt yourself a second before it starts hurting. And John Ramos, yes, I spent many years in college washing dishes, John. And in fact, my first job out of college was washing dishes at a Mexican restaurant. And you do get used to the hot water, don't you, John? In fact, you can sort of learn how to fight right through it. Okay, so this is the experience. And the reason that we sort of have these different sensations of pain and touch is because they are transmitted on different fibers, and these fibers have different speeds getting to our brain. Now, if any of you have ever been tickled or itched, tickling and itching travels really slow. Tickling and itching is brought up on slow fibers. And so tickling and itching takes a lot longer to travel from your body to your brain than does that time you got stabbed or cut yourself. That travels super duper quick. Okay? All right, let me see. That's all I wanted to cover today. We wanted to talk about these 4 other senses: hearing, taste, smell, and touch. I want you to know for the exam these different types of receptor cells. So hair cells for hearing, nociceptors for pain, thermoreceptors for heat, proprioceptors for touch. We've got taste receptors. You've got rods and cones. I want you to know all of these different receptor cells. And these cells are part of the nervous system, but they transduce external energy into patterns of neural activity. I then want you to know that all of these senses, with the exception of smell, travel through the thalamus to their individual processing cortices. I want you to know that auditory and olfactory are located in the frontal lobe, auditory in the temporal lobe, visual cortex in the occipital lobe, and sense of touch in the parietal lobe. I want you to know that the sense of smell is definitely intertwined with your limbic system, your amygdala, hippocampus, and temporal lobe, and that's why tastes, smells evoke such strong memories for each and every one of us. And I want you to know certain structures like what the semicircular canal and what the basilar membrane and cochlea do. I want you to know what the inner ear bones do, and I want you to know that balance is processed in the cerebellum. Do we have any questions about today's lecture? Sensation and perception. After this week, we're going to move decidedly away from biopsych, and we're going to start talking more about the mental side of psychology. So we're going to be talking about behaviorism next week. Any questions? Any questions? I'm going to go ahead and say goodbye to you. Holy cow, look at this backdrop. This is where I hope to be this weekend. I'm going to see a professional baseball game. I don't think I will be at Fenway Park. I'm actually going to Denver this weekend to see a Colorado Rockies game. But I'll be doing that this weekend. Hopefully you folks will be doing something fun as well. Okay, great. Thank you very much. Don't forget there is a webinar tonight at 8 o'clock. If you haven't come, you are welcome to come tonight. Don't forget your discussion board is due at 11:59 p.m. and your next writing assignment is due tomorrow. Any questions? Cool, Yanan. Thank you very much, Amber. Have a great weekend. Take care, Jordan. Hey, it's good to see everybody. Have a great week, and I will see you next Tuesday.